we're going to start recording, okay? And let me jot out some of the stuff. Okay, so from what I've written out so far for this exam, okay, we're going to have, I think, like 4 or 5 sections. Okay, so the first section, like always, is going to be our basics, in that we're going to be, you know, going over nomenclature and identifying or aromatic compounds. So identifying aromatic, non-aromatic, and anti-aromatic. Okay. We're going to have another section on, let's see. Just looking at the note that I made about it. We're going to have some reactivity questions. Okay, meaning we're going to talk about what types of reactions might form aromatic compounds. Okay, so we talked about this a bit in terms of you know, leaving groups leaving and making a molecule more soluble, or acid-base reactions. Okay, so let's just say ranking basicity of lone pair groups. What else do we have? Let's see, analyzing stability of intermediates for EAS or NAS reactions. And I think those are the things that come out now. Let me just want to make sure I'm being as clear as possible. Okay. That meaning still. Okay, we're going to talk about ranking reactivity for EAS and NAS. Okay. And then section 3 is going to be about drawing the product. Okay, I think there's going to be 6 questions here. And this one's just as simple as you are given the starting material, the reagent, draw the product. Okay, or draw the major product. Let's just say that. Major product. Then we have retrosynthesis, 2 problems. Just say 6 or 2 questions, and then 5, we're going to have mechanism, 1 question. Okay. It's going to be an NAS mechanism. All right. Okay. So this is the exam. Okay. So 5 sections. Let's just say I think the basics is technically 2 questions, right? Nomenclature, identifying reactivity. I guess we have 1, 2, 3, 4 questions. Okay, we're going to draw the products. That's 6 questions. So it's like 3A through F. 4 is 2 questions, and 5 is 1 question. Okay, so that is as detailed as I could possibly be without giving you guys the actual questions here. Okay. So to answer some questions, so just to circle back to what Anissa had asked before, she said, when we draw the mechanisms on the exam, do you want to see the sigma complex as well? And so the sigma complex is the resonance stabilization of the intermediate. If I ask about how stable is the intermediate, I would expect you to show me something about resonance. When I'm asking for you to draw the mechanism, excuse me, about NAS, I meant EAS mechanism. When I'm asking you to show me something about the mechanism, I would expect you to show me the mechanism in a formal way where you write each resonance structure individually, and you show me the formation of the electrophile, you show me lone pairs, formal charges, all of your arrows are there, and then everything is reacting with those arrows. The next thing you draw is the result of those arrows, and then the final product is drawn as well, okay? So those are the things that I require in order for you to get full points. Again, I'm being as clear as I possibly can in my direction for the exam, okay? So there should be no ambiguity about what is needed for what particular section, okay? Naranjana, so we're saying, are we supposed to know all of the mechanisms for all the EAS? So to just kind of get to the chase, EAS is one mechanism, the same way that SN2 is one mechanism. E1 is a mechanism because this is one mechanism. The difference is the formation of the electrophile for each of the mechanisms and the identity of the base that removes the proton in all of the mechanisms. And yes, you should know how to form the electrophile for each of the mechanisms if it's not already shown. For example, you don't need to show me the formation of SO3, okay? Sulfur trioxide just exists in fuming H2SO4. You don't need to show me that. And all of the others are formed in mechanisms that you've been shown, okay? So Anissa, now again, second question is, and what about Diels-Alder? Is that still going to be on it? Yes, there is one Diels-Alder question. It is somewhere in the exam, okay? It's your responsibility to recognize it and draw the product, okay? So it's somewhere in there. I'm not going to tell you where. Let's just say it's not going to be a part of the basics, okay? Obviously. So it could be a part of the retrosynthesis procedure. It could be a part of the drawing the major products like questions. I could just throw Diels-Alder in there. It's certainly not going to be part of the EAS mechanism, okay? But you should recognize the pattern for Diels-Alder, when it's appropriate, what the reagent is, which is mostly just the condition, and then how to draw the final product, okay? I'm not going to give you anything terribly tricky for Diels-Alder. It's going to be straightforward, but it's your responsibility to recognize that it's there and go with it, okay? Does that seem fair? Awesome, okay. So that being said, are there any major questions that you guys have been reviewing over this weekend that you wanted to go over during office hour? We could go over the EAS recitation worksheets. We could go over some questions from some of the homeworks if you guys wanted. What is on everybody's mind? What have you been working on that you want to talk about? Are there any aspects about nomenclature you guys want to talk about? Because I will say each of these sections is roughly equivalent in the number of points. I think they're all about 30 to 40 points each, okay? So the test is going to be 210 points again, okay? It's just the way it worked out. And I think basics is, let's just say basics is 40 points, reactivity is 60 points, drawing products is 40 points, retrosynthesis is 40 points, and the mechanism is 30 points. Okay, and again, that's where the points stand at the moment. So they're all about 30 to 50 to 60 points. I think the reactivity section is like obviously really important because that's the basis of orgo, right? Is being able to explain and think orgo. So again, that being said, any questions? Okay, you guys want to go over?
Can I share my screen for one question? It's on the slides.
Sure. Is it a slide? Let me see if I can give you the opportunity to share.
I'm sorry.
Sorry, I was just updating the shared preferences. So one moment. All right, I think you should be able to share your screen now if you'd like.
Okay. I was wondering if you could explain these three again, if that's possible.
Let me see. One moment. I see that you're sharing your screen, but I'm not seeing the actual share. So one second.
Oh, interesting. Okay.
Let me see. I might need to stop my screen share. One sec. Yeah, so I know that it still is my screen, so I'm just trying to see how I can get it to be near on Hannah's. One moment. So I'm going to stop share. Okay, so this is, oh, I think we just had yours for a moment. So why don't you
All right. Okay.
pull it back up one more second here, Hannah?
Can you
Cool.
see now?
All right. Yes, I can see it now. Okay, great. Perfect.
Yeah,
All right, so
are the ones that I'm still like confused as to I guess more so for these two, I'm still a bit confused as to like why this one's aromatic and this one is and
okay. So what about the first one that you underlined, the top right one, the pentadienyl cation? So tell me why that one is whatever you believe it to be. Let's walk through it because they're all similar.
Okay, so for this one, I realized this is sp2, so the p orbital will be empty, so you can have the electron flow. However, it's not Huckel's number, so it's going to be empty.
Yeah, exactly. So it should be flat, fully conjugated, and what's the word? Cyclic, right?
Yeah.
But we fail to meet Huckel's number, so it's anti-aromatic. And as you said, that carbon with the carbocation is sp2 hybridized. So if we look at aluminum or boron, aluminum, do you know where in the periodic table it falls? What group it's in?
I think 3 or 3.
Yeah, it's group 3.
Okay.
So if it has 3 valence electrons, how many bonds will it want to form?
3.
Yeah, and if it forms those 3 bonds, will it have any electrons left as lone pairs?
No.
Okay, so then what hybridization is aluminum?
sp3. No, sorry, sp2.
sp2, right?
Yeah.
So when we're bonded to 3 things, we have 4 orbitals that we can hybridize, right? 3 p's and an s. And so when we only need to be bonded to 3 things rather than 4, like carbon, then we only hybridize 3 of those orbitals, which makes sp2. And then we have 1 p orbital left over.
Okay.
So aluminum is like that, and boron, which is right above aluminum, is also just like that. Okay.
So would
these
you
are
say
both
anti-aromatic as well?
Yeah. So the aluminum cyclic one is the exact same configuration as the first one we went over, the cation. They both have 4 pi electrons. The aluminum and the carbon have an empty p orbital. And so everything can go flowing around, but it doesn't have the right number of electrons, so it's anti. And then meanwhile, the cyclic one with the boron in it, right, has 2 pi electrons, an empty p orbital on boron. So this is going to be then aromatic. Yep.
Okay.
Okay.
Okay. I guess it was not intuitive as like to if they had the p orbital empty or not. So that makes sense then.
Yeah. So again, if a p orbital is filled, it might be because it's already participating in a pi bond. If a p orbital is empty, then it could be used for resonance to become a part of a pi bond. And if a p orbital doesn't quite exist yet, but it's hybridized as sp3 and there's a lone pair there. So for example, like cyclopentadienyl anion, the one that's next to the one but with a carbanion rather than a carbocation, of the lone pair and the negative charge, right? So this one is sp3 at the carbon that has a lone pair on it. However, the lone pairs can shift into resonance and rehybridize to become sp2. And so that means the lone pairs will move into resonance. And so we have these three, or really like in this case, I'd say we have three potential conditions for these type of what electrons can do. So we have the empty p orbitals that we see on aluminum, boron, or carbocation. We see lone pairs that can shift into adjacent orbitals, like we see on the one we just discussed, that one right there, or on the nitrogen that we see next to us, or maybe all the way over on pyridine, okay, that nitrogen that's there, the lone pair that's not drawn, okay, which is on the nitrogen that's participating in the double bond, that lone pair is going to be outside of resonance, right? Because the p orbital on that nitrogen is already being used, and the lone pair is perpendicular to the p orbital plane. So it can't become a part of it. All right, so those are three possibilities of how orbitals can kind of play a role in, shifting in and out of these p orbitals, become aromatic, or essentially, aromatic. Okay, does that make more sense?
Yes, thank you so much.
Of course. Right, and then Nafisa is asking, can you go over the difference between anti-aromatic and non-aromatic? Okay, so just very quickly, and Naranhan, do you actually have the slides open by any chance? Because if you do, I think the slide maybe like right before this one covers the aromatic and non-aromatic one. If you wouldn't mind, maybe bringing that up.
I can bring it up. This is just a screenshot, but
well then don't worry about it. Then I'll bring it up. Don't worry. All right. So if you don't mind, stop sharing your screen, and I will bring up the aromatic stuff. So 1 second. Talk again briefly about it. So okay, I think this is it. Okay. All right, so we've got our different aspects about resonance, blah, 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 blah. Okay, so we've got our aromatic criteria. Okay, so notice we have our energy curve, okay, or not curve, but our energy, what's the word? Energy spectrum, I suppose we could say. Okay, where we're at our lowest energy down at aromatic molecules and our highest energy up at anti-aromatic. Okay, so these first three criteria, okay, are just for the sake of determining if we even get to aromatic versus anti-aromatic. Okay, the major difference between aromatic and anti is that aromatic is a very stabilized configuration where all of the bonding molecular orbitals are filled with electrons. Okay, other criteria that are required are that it's cyclic, it's sp2, aka fully conjugated, and flat. Okay, sometimes these two go together, but as we have found out that not all sp2 hybridized molecules are perfectly flat because they can distort themselves to misshape, and sometimes that's for the sake of escaping anti-aromaticity. Okay, because anti-aromaticity is a very unstable, high energy configuration for the orbitals, in which we have some of the non-bonding and anti-bonding orbitals filled with electrons because we have the wrong number of Huckel's electrons in the pi system. Okay, but they also, in order for that Huckel number to even matter, the molecule still needs to be in a ring as far as the p orbitals, needs to be cyclic. It needs to be sp2 because they all need that p orbital to be able to have a leftover p orbital to use. And it needs to be flat for all of the p orbitals to be parallel to each other. Okay, so again, we need something in a ring. We need everything to have a p orbital available, aka sp2, and we need all of those p orbitals to be parallel, aka it needs to be flat and planar. So all of them are not distorted at different angles. So if those three things are met, then we are looking at anti-aromatic or aromatic. Okay, aromatic is very stabilizing. It lowers the energy of the molecule, right? We were looking, I think, at the effect of benzene when we added a third pi bond, right? Cyclohexane by itself is, let's just say, our baseline. I add one pi bond, I get 120. I add two pi bonds, I get around 230. Okay, the conjugation effect, if we're saying, for example, I think we had said, look, we could have predicted 120. And then if we just double it, because we're adding a second pi bond, that's 240. Okay, but then there's some stability that comes from it being in resonance. Okay, and so we see the actuals around 232, 231. And so resonance stability is around 8 kilojoules per mole. Okay, that's great. We see a lot of stability, or a little stability. But then when I do benzene and I heat that for I hydrogenate it and I measure the heat released, okay, what I predict to be around 360, right? Because we said for every pi bond is 120, and 20 times 1 is 120, 120 times 2, 240, times 3 is 360, right? Well, let's just say I get even double the resonance. I should see a resonance stability of around 16. Instead, I see a resonance stability of around 152 kilojoules per mole, right? And so that's what aromaticity is. It's this stabilizing effect of all of my electrons. See the difference here? Being able to be in a ring shared equally among all of the p orbitals of a ring system, okay? So again, this is not always something that's desired if it's the wrong number of electrons in the system for the p orbitals to be able to handle, okay? So for example, cyclobutadiene is the wrong number. This is 4, okay? And even though we have 4 p orbitals, it simply is not going to be aromatic, okay? There's not, for a 4-membered ring with 2 pi bonds, we only have 1 bonding MO, okay? Which we know from looking at the frost circles, okay? Where we rotate the shape, put the vertex on a point, and we have 1 bonding MO, okay? That's it. All right. So aromatic means those bonding orbitals are perfectly filled. Everything is very stable. Anti-aromatic means it's either too empty or too full, okay, for us to be able to have that stability. And in fact, by not meeting the criteria and still being cyclic, conjugated, and flat, it actually becomes very unstable, okay? Too much of a good thing, let's just say that, okay, in terms of electrons, that is. All right, and then of course, you know, if we end up disrupting the ring, aka it's no longer cyclic, which usually would mean it would break, or we interrupt conjugation, perhaps by not allowing lone pairs to go into resonance, or by even distorting the shape of the molecule so that way pi bonds are no longer parallel to each other. Okay, not only does that upset the planarity of the molecule, but also those p orbitals are no longer in conjugation with each other because they're not parallel. Okay, so those are the criteria for each of them. Okay, so again, we go over these first 3 and then we say, okay, are these 3 met or are they not met? If they're not met, then the molecule is non-aromatic. If they are met, then we look at Huckel's number. And if we are at 4n plus 2 equals 6, n equals 1 in that case, then we're at a Huckel's number, right? 2, 4, 2, 6, 10, 14, etc. Okay, those are Huckel's numbers. For any numbers that are not that, so let's just say 4, 8, 12, etc., we're talking about anti-aromatic, okay? So again, that's the basics of what I expect you to be able to know in terms of identifying which molecules are aromatic or not. There are, again, I think one group of exceptions that I would expect you to know, which would be the annulenes, okay? So looking at our annulenes here, we see our 8-annuline, okay? The actual compound looks flat, but we know that it is not actually flat, right? 8-annuline looks like this. It's in a tub configuration, okay? And this is what I mean, by the way, when I say that the p orbitals are no longer in conjugation. Okay, these are, let's just say these red p orbitals are conjugated to one another to form this pi bond. But now these p orbitals, which again are conjugated to each other, are not going to be conjugated to the red. Okay, these are going to be separate from these. Okay, because this orange and this red are not parallel to one another. Okay, obviously same would go for this set of p orbitals, as well as this set in the back. Okay, pi bonds, pi bonds. Okay, but all of the others are going to be, or all of the double bonds themselves are going to be isolated. Okay, there's no longer going to be conjugation in this molecule because it's not flat. Okay, does that make sense? Hold on. Just 1 second. All right, and we're back. All right, so let's see. Awesome. Okay, so any questions to clarify that concept? Do we feel like we all understand and we can confidently, break down the difference between these three types of things and what expectation or what exceptions we would need to know? Understand? Okay, for those of us who came in late to the chat, if we go back to the whiteboard, just say, let's stop sharing this. If the whiteboard is still there. Yes, okay. So this is what we went over at the beginning. Okay, we went over what's going to be on the test. Okay, we have the basics in regards to nomenclature and identifying aromatic, non-aromatic, or anti, which we just went over. Okay, we didn't go over nomenclature, so if anyone has any questions about that, by all means, bring it up now. Okay, we also have our reactivity. Okay, this is going to be the biggest chunk of the test. It's only 4 questions, but it's 60 points of the 210. We're going to be talking about what some types of reactions that might form aromatic compounds. Okay, again, this comes down to you recognizing what an aromatic compound is or not. Ranking the basicity of lone pair groups in relationship to perhaps aromaticity. Analyzing the stability of intermediates for EAS and NAS reactions. And ranking the reactivity for EAS or NAS. Okay, so I'm not going to let you know which one of these it is, but you should know what would make a ring more reactive for EAS versus what would make it more reactive for NAS and how to rank it. The stability of the intermediates for EAS and NAS, well, that just has to do with, okay, I'm getting you a reaction and you're here to analyze the stability of the intermediate based on resonance of either the sigma complex or the Meisenheimer complex, and let me know which one's more stable. Okay, so if he's saying there's a homework question, why is the lone pair of imidazole more available than normal purity? That is a great question. So, and then Anissa will look at your question, and we can do some practice in terms of stability of the intermediate. Lone pairs on the imidazole. All right, so let's just actually practice this right here. We should have our Okay, and then pyridine. Okay, so we've got, why are the lone pairs of imidazole more available than normal pyridine? So we've got 2 lone pairs on imidazole, right? So let's just take a look at this. Imidazole, pyridine, or is it pyridine or pyrimidine? Hold on, excuse me. Yeah, pyridine. Okay. Cool. So we've got pyridine, blah, blah, blah. So obviously one of these lone pairs is going to be, let's just say, very unavailable. Let's just say we have A, B, and C. Which of these lone pairs is very unavailable for resonance, or excuse me, for basicity? Yeah, so the one that is very unavailable is going to be A. Why is A the least available for picking up a proton? Someone tell me why? So the lone pair is kind of, yeah, rather than saying it's involved in a pi bond, say that it's delocalized. And it's delocalized, I guess it's the only one that is delocalized, but what does that delocalization allow us to gain? Because it's very important. Can you say not involved in resonance? So involved in resonance and delocalized are the same thing, Justina, so you can say either. Okay, but the most important thing to describe about it is what Anissa and Nirhana are describing right now, that it is required to be delocalized so we get an aromatic ring. Okay, this lone pair group is required as a part of the 6 pi electrons for Huckel's number, right? We've got 2, 4, 6. Okay. However, if these lone pairs, B and C, are used, we don't compromise the aromaticity of the ring. Okay, so immediately we can already say A is going to be the least basic because it's required for aromaticity. Make sense? Hopefully. Okay, when it comes to B and C, well, we can analyze the conjugate acid and see which is more stable. Why don't we do that? Okay, usually when we're talking about stability, we talk about analyzing the conjugate. Okay, so let's just pretend that these reacted with some strong acids. Pick up a proton. The electrons go to the conjugate acid. Pick up a proton. Okay, and then we have here okay. So both of these are now protonated, positively charged. Okay. Are there any resonance structures I can draw that could possibly help me kind of stabilize or neutralize this positive charge? What could I do for these structures? because they're different. So they're going to have different resonance. Let's figure out what the resonance is so we can validate what's more stable. Any ideas? What's a resonance pattern I could use for, I mean, there's already a resonance pattern I'm looking at for both of them. The pi bond electrons go into the empty p orbital. So there's no empty p orbital, okay? Remember when nitrogen is protonated or positively charged, it doesn't have an empty p orbital, it's not sp2. Nitrogen is sp3. But this does match a resonance pattern in which I have a polar pi bond between atoms of differing electronegativities, okay? So I could potentially open this up. And there'd already be one lone pair here, so we'd get another lone pair. This would be negative, and this would be positive, kind of like opening up a carbonyl, okay? But in this case, our nitrogen would be positive, okay? So we can open this up for both of them. So let's draw that structure. This is positive. This is now got its lone pair back, so this is neutral. And then if I were to open this guy up, get this lone pair back. Positive, okay. What else can I do? Am I done drawing resonance now? And how to say you can make more resonance on the right, but not on the left. So no. Why don't we draw the resonance structures and compare them? Okay, let's do that first before we make any judgments. Okay, because it's not going to have anything to do with the quantity of resonance and more to do with the quality. Okay. So if I were to continue drawing resonance, can someone give me another pattern I can do rather than opening up a pi bond? What else can I do? There's more resonance for both of these structures. Yeah, so I could form a pi bond. Okay. I could form a pi bond when I have a lone pair next to an empty p orbital. Okay. So remember, there's another pattern. So this is one of them that we just drew. Okay. Another one is the opposite, okay, in which we have, just say, a lone pair next to, right, so this is just really the opposite of the structure of the pattern we were just talking about. Okay, which I can do right here. Okay, I could also move this via an allylic carbocation. Okay, so let's take a look at this one. Okay, I think Anissa has got it, but let's take a look. Versus here. So we look, if we were to keep going, we could do one more resonance structure for pyridine, in which we would move the pi bond again. Okay, but the most important thing here is not to do with the right having more resonance than the left. It's that the left structure, the imidazole conjugate acid, has a positive on this nitrogen when it picks up a proton. And we can also shift the pi bond electrons that are participating with this nitrogen at the moment to now be shifting into the nitrogen that otherwise wasn't participating in the pi bond. Okay, we can shift these two pi electrons and this lone pair in between these two nitrogens to basically share this particular configuration. This means that the positive charge, as Anissa said, is stabilized over two nitrogens, rather than in pyridine, in which it's stabilized best on the nitrogen, but then otherwise it's shared among three carbons on the ring. Okay, again, three carbons that are positive are still resonance structures that lack octets on all of the atoms. So they're not as significant of resonance structures as we see for, let's just say, these two, where all of our atoms have complete octets. Okay, we've got two great resonance structures versus only one good one, and two plus a third not so great one. Okay, so that's why the imidazole lone pair is more available to go pick up a proton than pyridine, because the conjugate base, or excuse me, the conjugate acid is more stable. And whenever the conjugate is more stable, then the reaction is more favored. Okay, whether it's as an acid or as a base. Does that make sense, guys? You feel good about that? Okay. Okay, so Anissa was asking before we got into this topic about practicing some stability of intermediate. Okay, so we can definitely do that. Does that sound good with everybody? Cool. Get a new whiteboard going. So stability of intermediates. So for this, we're going to have to look at some reactions. So we'll have okay, so we've got, you can just bring this over a bit. Let's do BR2, BR3. Do HNO3, H2SO4, and then let's do BH. Let's do okay. All right, so let's look at these three, and then we'll look at Nafisa's request for chapter 17 homework Q11. All right, so this is what I expect you guys to be able to do. for these types of questions. Okay, not only would I expect you to be able to draw the product, okay, but to analyze the intermediate stability. So if we look at this first one here, let's call it A. Okay, if you look at A, okay, what am I adding to my molecule? A bromine, exactly, right? So it's easy to know sometimes what it is that's going on. Now I need to confirm where is it going, okay? So I've got my nitrile group, okay? I'm gonna say, let's put the bromine on the meta position and observe stability, and let's put it on the ortho position and observe this, or excuse me, on the para position and observe stability. And we know that the ortho and para position share resonance. So let's do this. We're going to have our ring. Yeah, this is like what we did in class. Exactly. So if we only need to do one of these, then that's fine. But just so we all understand what's going on. Okay, this is like saying what I would expect you to be able to do on the exam. So let's look at para first, bromine. And I know technically, excuse me, this pi bond should go away. I can do that. Okay. Oh, not all of it. There we go. And then if I'm going to be putting it on meta, this pi bond. Okay, so bromine goes here, my positive goes here and here. Okay, and then I have to say, okay, well, this isn't the only resonance structure I have. I know that the positive moves around the ring. So for my para addition, my positive can also be here or here. For my meta, my positive can be here or here. Okay, which of these is better and why? Okay, this is what I would expect you to be able to do. Okay, does that make sense? Can anyone briefly explain to me which one of these is better and why? Use the terms meta and para if you can, which you should be able to. Okay, so we've got to vote for para. Why? So this is, again, which one is better and why? So tertiary carbocation forms. Okay. So is that the only thing that the nitrile provides, is the possibility for a tertiary carbocation to be there? Because what else is going on in the nitrile? What's going on between the carbon and the nitrogen? Is there any resonance in there? Okay, so I got to vote for now meta from Hannah, because the carbocation is not right next to the partially positive carbon on the nitrile group. And this is correct. Okay, we need to be mindful that, again, some of these groups are meta directors. And as long as we know that, then we can use that to check our work. Okay, so for example, a nitrile is a moderate electron withdrawing group. It means it's a moderate deactivator and it's meta directing. So in a way, I already know the answer is this. I just need to explain why. Okay, and the reason why is because my nitrile group is polar. The same way that my carbon nitrogen pi bond could open up for the imidazole and pyridine rings, we can open it up here as well. Okay, and so in this case, my nitrogen is going to be partially negative and this carbon is partially positive. Okay, and so here we've got this partial positive next to a positive formal charge. This is unstable. So we have positive next to partial positive, unstable. And here we have positive formal charge, avoids, or let's just say passes. What's the right word? Favored in order to avoid unstable like charges next to each other. I'm just trying to think of like English to describe this. Favored in order to avoid unstable adjacent like charges. Okay, I think this would probably be the best way to put it. I mean, if you put it in some similar way in different English words, as long as you're kind of getting to this point, then this is, you know, the right way we're doing it. Okay, again, usually meta is favored to avoid the positive being next to the withdrawing group. Okay, does that make sense, guys? Do we want to go through any more of these, or do we feel like we've got this? Again, we did this in class for a bit, so if we feel like we're good, we can move on to that homework question that Nafisa requested. Cool. All right, so let's move on. So let's look at the homework question. You get that for a moment. Okay. Just give me a sec. So we've got okay. So Q11. And so is this the question, Nafisa, the one that says in agreement with the bromination shown in lecture, which we did not discuss, by the way, phenanthrene is easy to reduce as shown below. Predict the reduction product of anthracene based on the predicted stability of the possible product. Is that the question you're talking about? Okay, all right, so let me just sketch this out briefly. Unfortunately, I can't do copy paste on Zoom unless someone wants to share that with me. Okay, so let's see, we've got anthracene. Okay, so if you guys remember, we talked about in lecture briefly, the idea that sometimes when we have a molecule reacting that is aromatic, we want the resultant structure to still be aromatic in some way, okay? So if I'm gonna do a addition reaction to a pi bond, what's possible is instead of doing EAS, I do an addition reaction that still preserves aromaticity, but it's broken up in two different parts of the ring. So for example, if we're looking at, let's see, anthracene, like this, okay, we've got, or excuse me, phenanthrene, my bad, this is phenanthrene. If we're reacting with H2 palladium carbon, okay, I'm gonna want to reduce one pi bond to add some hydrogen across that pi bond, the same way that this happens for something like this. Okay, if I use the same thing here, all I'm doing is adding hydrogens across this pi bond. Okay, on the same side, it's an addition, that doesn't matter here. Okay, so we're going to look at the other compound in a second. Okay, I'm just trying to explain what's happening. All right, so we use this pi bond, okay, to react because this preserves aromaticity in two of the rings. Okay, so we have these two kind of like benzene rings preserved. Meanwhile, here I have a hydrogen being added, and here I have a hydrogen being added. Okay, for anthracene, okay, which is this kind of more caterpillar looking ring system. Okay, the pi bond that is going to be isolated is a little bit less obvious. Okay, but if I'm doing this same thing here, and a better way to do it is instead of using H2, let's use Br2. Okay, let's use Br2 and see how this works. Okay, because this is what Dr. Hammer's using a lecture, and we can then kind of like extrapolate to what hydrogenation would give us. Okay, so the idea here is how can I use a pi bond and still maintain aromaticity. So one pi bond and still maintain aromaticity for my ring, okay? And meanwhile not have like extra pi bonds that might destabilize the compound, okay? So in this case, we have a couple of possibilities. Okay, I think Dr. Hammond like plays it out in his answer key, okay? But we can kind of say, all right, we can use, just maybe cut to the chase, we can use this pi bond here, react with bromine. Okay, so I'll put Br here. Remember, this is a positive bromine. Okay. We want to draw out this mechanism for the sake of drawing it out. Boom, 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 boom. These electrons come attack Br. Pi bond circles back, attacks again. Bromine leaves. Okay. Then we have this bromonium bridge, which we know could open up as long as we have a stable enough carbocation. Okay, not only do I have a tertiary carbocation that could exist at, not all of it, at this position, but it is also allylic in resonance. So what could happen is then we resonate this partial positive charge around the ring. And then we end up with boom, 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 boom. Our bromine and our positive is here now. Okay, so the bromine that left could then bind there. Okay, and so this is a similar reaction, or at least a similar logic to what not only happened in Dr. Hammond's version of the lecture, but also what he's talking about in the homework. Okay, and that these two positions are the most vulnerable for not only bromination, but hydrogenation. Okay, we'll have a bromine here, and then the second bromine will come and attack at the carbocation. And then we end up having two isolated aromatic rings. Okay, so this is a complicated reaction. I wouldn't expect you to do something this crazy on the test. Okay, but I do expect you to understand the logic behind it. Okay, again, this reaction undergoes an addition of bromine, sacrifices a pi bond, but we still have 6 pi bonds, two aromatic rings. Okay, here we had 3 aromatic rings, or really one aromatic system. And we had 1, 2, 3, 4, 5, 6, 7, so 14 pi electrons. Okay, technically that is a Huckel number. Okay, here if I just had 12, okay, there's no way that 12 by itself could be a Huckel number. So instead of keeping them all together, I move them into 2 separate rings. Okay, 6 and 6. All right, hopefully that makes sense. Okay, Niran is asking what I expect you to know all of the reactions from the last exam. I mean, I would expect you to know them for the sake of the fact that your final is going to be in a few weeks. It's not, yeah, in a few weeks. So I would say keep them still at hand. Am I going to be testing you on them? Mainly, no. I mean, as I said, you will have a Diels-Alder reaction tucked into this exam as kind of like a retribution question because so many of you either skipped it or did not get it correct. Okay, I'm not going to be testing you about Diels-Alder to the most difficult extent. I just want to make sure you guys understand the pattern, recognize it, know how to draw the products, including stereochemistry. And again, I'm not even going to ask you about endo versus exo. I'm just going to ask you about how to draw the product, okay, for Diels-Alder. And it's going to be incorporated into one of the sections of the test. I mean, I definitely expect you guys to still remember oxidizing reduction, Grignard reagents, simple SN1, SN2 reactions. Am I going to be testing you on those mainly? No. Okay. Okie doke. All right. Anything else, guys? Take a look at the homework and see if I can give you guys any recommendations. Obviously, number one is super important. Just understanding how to name stuff. Number two, likewise, drawing it from the name. I'm not going to do anything about isomers this time. Question 4 is obviously super important. Keep in mind that there are way more examples than what Dr. Hammond provided in the answer key. Okay, those are just some examples. We talked in class about number 5 in terms of the geometric isomerism. Question 6 and question 7 are great examples of basicity of lone pairs, and we kind of talked about that already with pyridine versus imidazole. What else? 9 is super helpful. 10 even helps explain kind of this idea of reactivity of aromatic compounds versus non-aromatic compounds, and that the answer for the aromatic ring is still going to preserve aromaticity, whereas for the non-aromatic ring, it did not. Okay, so just keep that in mind. And that's just for the aromatic homework. All right, otherwise, again, as I said on slide 1, all right, I couldn't be more clear on what it is I expect you guys to know. Okay. So, any more questions, guys? Again, if you haven't gone through the homework for chapter 18 or 17, I recommend you do that for the next couple of days. Okay, some of the questions obviously are going to be a little bit trickier. Always the last couple of questions on each homework are very difficult. Okay, it's supposed to be something that you struggle with. And I wouldn't say that our exam is going to be that hard, certainly not. Okay, Nafisa saying, can you go over Q10, second reaction, Q10 of the same homework of chapter 17? Yeah, let's take a look. All right, so we've got chapter 17, homework, Q10, let's just say this, perfect. Okay, so we're given a comparison of these two different reactions. Okay, so let's just say, I'm just going to draw this first one, not go through it, but we just look at what the product is. Okay, so cyclopentadiene with the Br2. We've got our kinetic product, which is just the addition of our bromine. Okay, and we also have the possibility that if Br behaves as leading group, then one of our bromines could leave, and we'll end up with a resonance stabilized carbocation that can then resonate, obviously, and allow our bromines to be a little bit further apart from each other. Okay, when our bromine can come in and attack. Oops, gosh, sorry, I'm bad at drawing pentagons in one shot. Okay. And let's just say we have a preference for it still being trans, so they can be farther apart from each other. Okay, so we have our kinetic product that happens very quickly, the same way that it usually does with an alkene addition on a pi bond. Then we have a thermodynamic product, which is a little bit more stable because the bromines, which are large atoms, are farther away from each other. Okay, and Nafisa, however, is asking about the second question, in which we have an aromatic compound reacting with Br2. Okay, so if this was us getting the same thing, okay, Br2, okay, we could theoretically form the same kinetic product. Okay. What is bad about this transformation for this particular molecule? Why is this not a good payoff? Yeah, exactly. And so we lose aromaticity. All right. We were a happy aromatic compound, stable compound. Not a good payoff because we have now lost aromaticity. Okay. So how could we potentially get aromaticity back? Okay, like we normally would see in some of our what's the word? In some of our what's the word? EAS reactions. Okay, and this is by, instead of the second bromine actually binding, this bromine or the other bromine perhaps might leave. Okay, so let's just say we see one of our bromines leaving. Or we might have the other bromine leaving. So this is nice, okay, because it allows us to use the bromine to then do kind of an EAS reaction, okay, where one of the bromines has been added, one of the bromines has left, and now the second bromine that has left can behave as our base, okay, rather than like FeBr4 or water plucking off a proton, right? We can use Br to pluck off a proton where our new nucleophile added, okay? Which of these two resonance structures is more stable? The one in red. So why the one in red? We certainly have the ability to do the lone pairs into the pi bond, right? So this is nice, we can do this. Okay. And what about the resonance of the black one? We know I can do this. Pi bond here, positive. Oh, I guess we could also eventually do the same with the black one too. Yeah, see, when we draw out the resonance, we see not only do we get the ability for the oxygen to bear the positive for both structures, but we also have an additional resonance structure for the black, okay? So we're gonna be able to have the lone pairs come into resonance for both of these situations, but only the black one has the ability to take advantage of that pi bond in the ring. Okay, so what does that mean about what intermediate is gonna be favored? The red intermediate or the black intermediate? The black one, right? Because we've got more resonance, it's just as good. We still get the oxygen bearing the positive charge in both. So it's not as if one of the resonance is better. It's just that we have one more carbocation resonance structure for the black intermediate. So it's going to be more stable for this bromine to leave and for the dashed bromine, the one I drew on a dash, to stay behind. Okay, so then the last part of this mechanism is going to be the bromine that got kicked off, coming back and doing an EAS mechanism where we pluck off the hydrogen so we can substitute the bromine that just added for the hydrogen that we're removing. And form pi bonds here, and we just keep moving the resonance around. Oxygen. Okay, so this is just an EAS mechanism where we have substituted the hydrogen at this position for a bromine. Okay, so this hydrogen got substituted for this guy. Does that make sense? Again, EAS here is a possibility as a mechanism because this is an aromatic ring. We want to preserve that aromaticity, so we do something a little bit more complicated but special with this molecule than we would with just cyclopentaldiene. Okay? That make sense, guys? If you can understand this one, then I promise you'll be fine. Okay, even if you don't understand, there's not going to be anything this like complicated on the exam. Okay, don't worry. Okay, I've learned my lesson. Our exam's going to be a little bit more straightforward. It's still going to be a little bit challenging, but not as challenging as the last test. Okay, so I just want everyone to be able to complete it, and then we'll go from there. Does that make sense, guys? Everyone feeling okay? Any last minute questions? Of course. Okay, let's take a look at that list one more time, just for those of us who maybe called in late. No problem, Nikisha. Okay, again, guys, so go over your nomenclature. Please don't lose points just because you don't know how to name the benzene derivatives. Okay, please know which benzene derivatives are more important than others. Okay, we already went over how to define aromatic, non-aromatic, and anti. The directions in this section are very clear, so don't worry about ambiguity. When it comes to reactivity, again, we're going to do what we did in class, which is we're going to be analyzing the stability of the intermediates. We're going to be ranking reactivity based on nucleophilicity or electrophilicity of the ring. We're going to be ranking basicity of lone pair groups, which we did right here on this page with imidazole versus pyridine. And we're going to be talking about types of reactions that could happen that might form aromatic compounds. Okay, so again, you need to know how to, what reaction a molecule might need to undergo in order to become aromatic. Okay, and then drawing some major products, retrosynthesis, like we did in both of these are like our recitation homeworks or assignments, and then a mechanism, which is just basically straight from the book. Okay, by basicity ranking, do you mean looking at the conjugate bases or acids? No, Hannah. So I mean, like, for example, if we're looking at imidazole and pyridine, and I said, okay, looking at lone pair groups A, B, and C, rank them in order of basicity. Okay. And so, for example, A is the least basic because it's required for aromaticity. So it's going to be the least available to go pick up a proton, basically being the worst base. And then between B and C, B is the best base because it has the best, most stable conjugate acid resonance. When the conjugate, whatever, is more stable, that means the reaction is more favored. So as we see here, the conjugate acid is more stable. That makes this a better base. Okay, so it would go A is the least, C is the middle, B is the best in this case. Does that make sense? Awesome. Okay, guys, anything else? Are we ready for our test on Tuesday? I have a feeling you guys are going to do pretty well on this one, okay? If we've got nothing else to discuss, then I'm happy to end a little bit early if you guys are. What do you want to do? You feeling good? Awesome. Okay, guys, good luck with the rest of your studying. I hope this was helpful, and I will see you all on Tuesday, okay? Please sleep well and enjoy your July 4th, okay? Do a little bit more studying if you feel like you need to. All right, and feel free to email me if you have any questions. But of course, as always, please reference your book and the answer key before you email me, okay? All right. Okay, guys, I will upload the recording once it stops buffering or whatever it's called, or rendering. And you can, obviously watch it on YouTube later if you care to, okay? All right, guys, see you Tuesday.